all the laws of physics that you have ever discussed or about to discuss is nothing but some kind of conservation equations. Yeah, from our prior knowledge, you can understand that there are three fundamental things that are conserved. We say mass, energy, and charges are actually conserved. What this means? This means that one cannot destroy these three things and also one cannot generate these three things. They can only be transferred or transformed from one system to any other system. Kirchhoff did the same hypothesis and comes up with his two laws. In this video, we'll understand the Kirchhoff's current law first. Current law is nothing but the conservation of the charges, that one cannot create the charge or destroy the charge. We just have to use their energy. For that, you can understand that if we have the combination of multiple wires or the conductors in which the current is flowing, the net amount of current will remain constant. Means we can say at any junction point there will be no sink and source of the current, then the net current coming in needs to be equals to net current going out. Let's try to understand it. You can see, suppose here I have three conductors. I have drawn three conductors and this is nothing but their junction point here. If I say that current I1 is coming into this junction point, current I2 is also coming into this junction point, and there is one current leaving this junction point is I3. As we were discussing, that net amount of charges flowing in needs to be equal to the net amount of charge going out per unit time. Means this whole current needs to be constant. What I mean, I should write it in an arithmetic form. Arithmetically, what I'll get? I'll simply get I1 that is coming in plus I2 that is also coming in needs to be equals to I3. This is what the basic Kirchhoff current law is. Now, it doesn't matter how much conductor you are adding. Let's say now I'll add one more conductor here. In this, the current is flowing in this direction, I4. Let's add one more conductor here. In this, the current is flowing in this direction, let's say I5. What we'll get? Again, to satisfy this law, we just have to write that the net current flowing into this junction point needs to be equal to the net current flowing out of this junction point. Again, the same logic that the charges will remain constant. What I can write for this second situation? Again, following the same, that the net current coming in needs to be equal to the net current going out, following that we have the net amount of charge is conserved. What I'll write what is the net amount of current flowing in? We have I1, I2 and I5 coming in. So let's write it out here. We have I1, I2 and I5 coming in. Again, what amount of current going out? It's only I4 and I3. As you can see here, only I4 and I3 are the currents that are going out. Let's write it out on the right side. So we'll get I4 plus I3. This is what we get from the Kirchhoff's current law. I hope you got the concept. It doesn't matter how much current we'll join or how much conductors we'll join at any junction point. Let's try to understand it with a simple example. Here you can see a mesh. In this mesh you can see that there are multiple conductors joined together. Let's try to calculate the current. Let's start with this value of I1 first. So for this I1, what I can write? Let's say the I1 is in this direction and we have I4 in this direction, and let's say I3 we have in this direction. So what we'll write? We'll simply write, I'm completely letting the values in my point of view. But what I can write, I1 coming in, I4 is also coming in, thus I3 needs to be go out. I cannot let all the three currents coming in, because if I do so, then where the net amount of current will go? Thus, I can let these two I1 and I4 that are coming in, but I have to let that I3 is going out. So first equation that I can write is nothing but I1 plus I4 needs to be equals to I3. This is our first equation. Now, this we have written for the junction point C. Now, let's try to write the equation for the junction point D. In junction point D, let's say this is the second equation. In junction point D, you can see here what is happening. In junction point D, the net amount of current going out is 5 ampere, and this I4, because I4 also is going in this direction, that we let in this direction. So what we get? We get 5 ampere going out plus I4 going out, and what amount of current is coming in? It's this 8 ampere coming in. So let's write it out here, 8. So we'll get the value of I4 from here is nothing but 3 amperes. This is for the junction point D. Now, one more thing, we can generate a relation. Let's try to write for junction point A. Let's say we have this third equation for junction point A. So at junction point A, again, following the Kirchhoff's current law, what amount of current is going out? 8 ampere. This I2 is also flowing in this direction. So I2 and 8 ampere both are leaving the junction point, and coming in current is 15 ampere. So what we can write? We can write 15 is equals to 8 plus this value, that is I2. What we'll get from here? We'll get I2 is nothing but 7 amperes. Let's say we have generated this equation for junction point A. Now, similarly, we can write for B. In this B, as you can see, we have the 3 ampere current coming in. I2 is also coming into this junction point B, and one more current, that is I3, is also coming in junction point B. That is not possible. It means I3 should go out. What we let the value of I3 is actually wrong. Let's try to write it. So for B, at junction point B, this is a fourth equation. We have to write that the I3 let value is wrong. I3 needs to be coming in. So we'll take I3 in the negative direction. Here, let's write it out here. So I2 is coming in, 3 ampere coming in, I3 is getting out. So I2 is coming in, 3 ampere is coming in, but I3 is getting out. So what we get here, I3, I2 we have generated, we got 7 plus 3, and I3 we'll get as 10 ampere. This is what we got for which junction point? For B junction point. Let's write it out here for B junction point. Now, for all the junction point, we have applied the Kirchhoff's current law. Let's try to see this equation again. I1 plus I4 equals to I3. But at this point of time, I3 comes out to be negative. Means I4 is coming in, I1 is also coming in. This I3 comes to be coming in, but that's not possible. Thus, if I apply all the values, we have the I4, we have the I3. Let's write it out here. So I4 we know is positive, means what we let for I4 is actually correct, means it's coming to the junction point C. For I3, I'll say that it's also coming in. This I1 needs to be go down. So what I'll write, I1 is equals to I4 plus I3. What is the value of I4? We have calculated here is 3 ampere. For I3, we have calculated 10 ampere. Thus, we'll get I1 is nothing but as 13 ampere. So it doesn't matter how much conductors you have. It doesn't matter how much junction points you have. For any mesh, you just have to apply the Kirchhoff's current law, satisfying that there will be no loss of the current, there is no sink and there is no source. The net amount of current coming in needs to be equals to net amount of current going out. Well, that's all for this video. I hope you understood the concept of Kirchhoff's current law. In the next video, we'll talk about the conservation of energy, and we'll try to understand what the circuits are. Well, till then, keep learning and keep exploring.